Starting from this point, everything will be a lot easier to do. I'm going to make a very simple rectangle collision on the pedals. Let me open the game and show you what I mean. The ball is a rectangle and those pedals are a rectangle too. And so the ball, for the left pedal, the only line we are interested in, or the only edge, let's say, of the entire rectangle is the very rightmost line. If the ball were to collide with the top or the bottom line, we are not interested in that collision. And the same thing here. The only edge that we are interested in is the leftmost edge. All the other edges of this rectangle are not important to us. So we need to make sure that the ball, when it collides with one of these edges, is properly reflected as if it was the screen edges. And in order to do that, we need line intersection. Let me draw you a simple picture. Let's say this is our pedal and this is our ball. Actually, let's move this a bit to the left here. Now, let's say the ball is moving in this direction and the line we are interested in, the collision line, is this one here. The green one. We want to collide with this one. Now, if we make the ball fast enough, we can make it so that the ball within one frame goes from here past the line. And then we don't know if it's actually colliding with the rectangle at all. Or if a collision happened. We don't know if it came from this side, you know, any other side, like reflected back towards this. We don't know. And so what we need to do is cast this into the future and then look if the line from the past to the future intersects with the line we are interested in. And this brings us to line intersection. If you like what I do, consider tuning into my Twitch. I stream at 10 a.m. Central Eastern Time, which is 1 a.m. Pacific Daytime. If you want to directly support me, you can do so via Patreon. This will give me more time to work on my game, Cakes to the, and you will get reading access to the GitHub repository. Patreons will also be called out at the end of every video. Subscribing and leaving a like also helps a lot. Thank you very much for your support. So thank you to Felix F and Meo the Writer for being the first supporters on Patreon. Now, since this is a programming channel and I'm not a math genius, I will link to a video in the description that I used to understand how to do line intersection in 2D. To give you a very simple explanation on how the line intersection will work, let's say we have 4 points. So basically we need 2 lines and those 2 lines are made out of 4 points. Let's say this is A, this is B, this is C, and below here we have D. Line intersection looks at the line from A to B and the line from C to D and tries to generate values T and U that are within 0 to 1. So basically you scale the vector A to B by T and you scale the vector C to B by U, and that results in a collision point. That's the idea, and that collision point would be here. So the vector C to D would be scaled like this by U, and the other one would be scaled by T. One of those variables is enough to get the point that we are interested in. And if these values are outside the range of 0 to 1, we know that either they don't collide at all, or we know they collide later, but we are not interested in later. We are interested in now. Quickly skipping over the entire math on how to do this, it's a bunch of dot products and stuff. I have yoinked a function from the internet that we will put into my math.h. And this is going to be the only function that we are not going to write ourselves. If you're interested in how the function works, feel free to check out the video in the description, this detailing how it works. It's not actually that difficult to understand the math behind it. And if you want, knock yourself out. Okay, so this is the function. Quickly going over a couple of points. First of all, the cakes assert does not work here. We need to include the logger.h. Then we can assert on the collision point. We need a new operator for minus. Quickly create one on the vector 2. And that actually takes in another vector, which would be other.x, and then minus other.y. This is going to be a vec2 other. And looking down here, we need to do vector addition, a plus r, to get the collision point. This is basically the collision point I was talking to, r times t, while r is a to b, right? And the scaling is t. And the front part, a, just means, well, from this point on, that vector, right? Because we need to offset. We need the a for the offset. Okay, so we need to do vector addition as well. That's going to be x plus here, plus and plus. Okay, we should have covered everything we need. Looks good. Then we switch back to the game, into update game, and we look below where we calculate the ball boundaries. Let's create a new local scope here. Check for collision with the pedals. Okay, what do we need? First of all, we need to look into the future. So a vec to next ball position, that would be, and since we finally have operators, we can just do e origin plus e velocity times delta time. Now this is a small trick here. I need to get the entity pointers for the left pedal and the right pedal. And I know, since I created them in init, we know the first one, the first entity of the game state is going to be the left pedal and the right pedal is the second one. We need those to calculate their bounding boxes. So a rect left pedal bounding box is get underscore bounding underscore box. Takes in the left pedal. We don't have this function yet, but I'm going to create it in a second. And the right pedal bounding box is getting the bounding box from the right pedal. Let's quickly create this function. Go up above init game. And I suppose we can put a small section here. What I love to do is put these in nicely formatted comments. Functions related to the game. Because these functions, they get material functions. They are more or less rendering things, and we will restructure those in the future. These are just related to the game. And below that, we declare the internal. Let me center this a bit. Get bounding underscore box. Takes in an entity pointer e. The first thing it does, it asserts on the entity, no entity supplied. This is just for programming purposes to make sure, oh, and I forgot the return type, that's going to be a rect. To make sure that we supply something while we are working with the game. Okay, and then we return a rect that is e origin plus e bounding box dot offset and the e bounding box dot size. Very simple. Put this in one line. Okay, back in the update game function. This is where we actually have to check if we want to do collision. And this is going to be a simple if check first. Well, the origin of the ball is very important here. X. We only check for collision if the origin of the ball is greater than the left pedal bounding box position on X plus the left pedal bounding box size on X. That will make it so that the origin, the middle of the ball, will never be checked for collision once it had already passed the line, meaning it is the middle point of the ball is past the outermost side of this left pedal. But this is not enough. We also need to take into account the size of the ball. And therefore, checking against the origin is not enough. We also need to remove the ball's bounding box. And so on top of this, we are going to move the bar even further to the right, saying that, oh, the ball, so the e bounding box dot size on X divided by 2 is also important. Technically, we would have to do the same thing as above, add in the origin, then the offset of the bounding box, and then add in the size without dividing by 2. If you want to do that, actually, let's do that real quick. We add in the e origin dot X plus e bounding box dot offset dot X, and then we add in the bounding box size. Oops, I forgot a plus here, which, as you can see, is very long. And so I would love to extract this into what is called a left barrier. The float left barrier is that. And so if the origin is greater than the left barrier, we are golden. And it also needs to be origin dot X needs to be less than the right barrier. What we are going to calculate next. That is a float right barrier. It takes the right pedal bounding box position on X and removes the e origin dot X plus the e bounding box dot offset dot X plus e bounding box dot size dot X. That is the right barrier. If it's within those two barriers, then we want to do collision detection. Otherwise, it's passed and we already lost. Or the enemy already lost, right? Since we now know we are in the collision area, let's first check for the left barrier. Left barrier check, I suppose. We define a vec2 collision point. Assign that to 0. And then we do if we have line intersection. And now the points are important. We take the origin, then the next ball position. And the vector C is going to be a vector 2 from the left barrier on X, that is the position on the X-axis, and the top part would be the E. The top part is the left bounding box dot position dot y. This is going to be the first point, and then another vec2 from the left barrier down to the left pedal bounding box dot position dot y plus left pedal bounding box dot size dot y. Don't forget to supply the collision point as an address, and we can check what we need to do. We basically do the same thing with the screen. We invert the velocity on x and remove the penetration times 2. So the first one is easy. E velocity dot x is minus e velocity dot x. The next part is remove the penetration. That is just the next ball position on x. Need to add in 2 times the left barrier minus the next ball position on x. And as you noticed, we will be using the next ball position further down instead of the hard-coded velocity addition here. That is the left barrier check, and then we do the right barrier check. And we can basically copy most of this, but I guess we just write this out. We take in the vec2 collision point, assign that to 0. And then do another if check, line intersection, takes in the E origin, and then next ball position. Then we do a vec2 again, this time the right barrier, take in the right pedal bounding box on Y, and another vec2, right barrier, right pedal bounding box, position on Y plus right pedal bounding box, size on Y. And don't forget the collision point. We invert the x velocity and do the same thing. Then we remove the penetration. That would be the next ball position on x. Minus equals this time 2 times the right barrier minus the next ball position on x. And I think it needs to be inverted. Next ball position minus the right barrier. Right, since the next ball position is further along than the right barrier, we need to invert that distance. So that would be the right barrier over here. Once all of this is finished, let me double check here. This is the check for the left and right barrier. We set the E origin to the next ball position. Will that work the first time? No, it never works the first time. Lol. But we can try. Yep, it didn't work. Or maybe it does. No, it doesn't. Oh, I found the issue. I'm an idiot. We only need to add in half the bounding box size, and we don't need to do any shenanigans with the offset and origin and all of that stuff. Assuming this is the left barrier and the ball would be colliding on the origin, the only thing we need to do is move this left barrier by half the size of the collision rectangle. This moves the barrier further to the right, and then we can do a simple origin collision here. That's what we need to do, and that's why we don't need to do any offset. I was just confused. Yeah. So remove the offset and bounding box, offset and all of that stuff, and just add in half the size of the bounding box for the ball. So the E bounding box size on X divided by 2 on both of those barriers. Now I want to check if that works. Okay. What? Okay, I found the other issue why it didn't collide. This over here, the origin plus velocity, this has to go. We are adding velocity here. Add velocity. Like this. This is for the ball. For the left pedal, we just add in the velocity like this. E origin plus equals E velocity times delta time. I forgot I don't have a plus equals. I don't want to create one right now, so do it like this. E origin is E origin plus velocity times delta time. And now we should have a proper collision. It is not perfect, and I'll show you what I mean by not perfect. If you want to, you can improve this. Let's say this is our ball and this is our pedal. Right now we are colliding the origin point, which is the middle, with the pedal. And so we would be colliding for every single point that goes along this line, right? But if we were to move this way, we are not colliding. But in actuality, if we move this, placing this over, we actually would be colliding here. And this is the downside of this approach. We are missing the pedal here, even though we are visually colliding. The improvement over this, and I want to give you this as a homework, instead of casting from the middle, well, we should be casting from the top and from the bottom. And then in the other direction, of course, taking the top and the bottom of the other side. So yeah, do that as a nice exercise. It's definitely helpful to do so. Okay, back in the game, there's 2 more steps. We need to increase the ball speed over time. That was the last homework. And we need to make this pedal move wherever the ball is. Let's increase the speed first. That's very simple. we go where we have the ball component. After we applied the velocity, create a new scope here. We increase the speed of the ball. First of all, we need a float speed up. And I put this to 50. Ctrl F. I've been testing around with this and that value was good. Then we check if the E velocity dot X is less than 0.0f, less than 0, then we remove from the velocity on X the delta time times the speed up. Need to write speed up correctly. And in the else case, we don't remove, but we add in. We do the same thing for Y. Copying is fine here, I would say. It's only like 3 changes. Quickly double check if that works. Let me undo the Y velocity here real quick to see if the ball increases in X speed. It seems to be getting faster. Yeah, it's getting faster. Okay. Yep, that's definitely faster. Boing, 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 boing. That's good. That's good. I can move out of the way. I can try to hit the perfect... Yeah, this is the issue that we have, right? We are actually colliding, but we are not. So yeah, if you want to fix that, do that. Very nice. This speed up is a bit too much. I think a 25 speed up would be better. If you want more, you do more. I also add in the Y velocity speed up. And then back in init game, down here, where we set the ball velocity on X, we also add in the 250 for the Y velocity. Now the last part is to make the right pedal follow the ball. And I suppose I put this below the left pedal if has component E component right pedal. First of all, we set the velocity to 0 again, I suppose. Then we need to get the entity ball. And I happen to know, of course, that it's in the game state entities on 2. Obviously, you would want to do this better in a better way, but that's fine as well. Since this is a small game and we don't need to find a lot of entities, right? We know what we have. Okay, so how do we make the pedal move? We need to check the origin relative to the ball origin. And there can only be 2 options. It's equal or it's not equal. Not equal is the one we are interested in. On the equal part, we don't do anything. On the not equal part, we check if it's above or below. So let's do the first check. If E origin.y is greater than ball origin.y. Then we need to set the E velocity to speed, I think. Let me double check in my brain. Our origin is greater, so we need to move down because the ball is further down. Actually, we need to do minus. Our origin is greater, so it's further down, so we need to move up. And since Y is 0 at the top, we need to decrease our position. Then we create a float Y heading. That is the E origin.x.y plus equals E velocity.y times delta time. That is the heading. This is what we are going to be moving. And then we also need to get a float distance in Y to the ball. And this is the ball origin.y minus E origin.y. Both of these are negative values, and then we can check the one that is shortest we take. If the place we are heading to, the Y heading, is less than the distance to the ball, we need to set the E origin.y to the ball origin.y. Why do we check if it's less? Well, a more negative value is greater in absolution. But yeah, we're basically making sure that we are not overshooting, right? Oh, the ball is right next to us. The heading is actually on top. Then we move to the heading. And then next frame, oh, it's further below than us. We need to move down and we're overshooting. And then like this jittery thing happens. We want it to be smooth, right? We want to go here and then the last jump has to be the exact position of the ball. That's what we are calculating here. And so that is the first case. And the other case is if the E origin.y is actually less than the ball origin.y. Well, you guessed it. We set the velocity to plus speed. Then we create those 2 again. Let me label those real quick. We are below the ball, need to move. And this is where we are above the ball. We are above the ball, need to move down. The ball is below and we are removing from the ball origin our origin. And those are 2 values that are greater than 0. And then we do a simple check. If the Y heading is greater than the distance to the ball. This time we check for greater. Well, we set the same as above. We set the origin to the ball origin. Quickly build and run if that works. And now the right pedal should follow the ball. And it does. And it doesn't do that. anymore. Wow, I think I copied, or did I do plus equals here? That's dumb. It's just supposed to be plus here. There was a mistake. The origin plus equals velocity on the heading calculation. Wow, another issue. We actually set the x velocity here. We need to set the y velocity. I'm sorry. I forgot. We need to put an else case here, and then we need to apply the e. Origin dot y is y heading. And I do the same thing here. Okay, that looks good. Okay, so the downward velocity of this guy is too quick. I'm doing something wrong with the downward velocity here. Sadly, I don't have more time. I will now need to do the Git stuff. This is more or less what I wanted to show you. I'll fix the error later. So I guess we'll do git add, git checkout minus b 13 underscore font atlas. We're going to do font next. So stay tuned for that. It's very important in our game. And then we do git add dot git commit minus m, edit a computer to play against, and collision detection for the pedals. Push minus u origin 13 font atlas. And that's it. Thank you all for watching and see you next time.